We now consider a two-dimensional example. We imagine a circular oil slick that's on the surface of the water, and like many oil slicks, it would have different densities of oil. In particular, the density of oil would be high near the center, and then it would decrease as you move outwards. So we have a circular oil slick, and the density depends on the radius, or the distance from the center out to some point. If we want to know the density of the oil on the water, we can use this formula here, 100 minus r squared over 10. Notice the units, kilograms per meter squared, so this is pretty reasonable. We would say if I cut out a meter of surface area here, or took a meter squared of water and fenced it in with buoys, here's how much oil I would have, and kilograms is a pretty natural unit for that. So if you're not entirely comfortable with units of density that aren't kilograms per meter cubed, which is the most traditional way to see it, just think of the context. Here, if we box off some part of the ocean, we can find a certain number of kilograms of oil, and so kilograms per meter squared is an entirely reasonable unit of density of oil. Okay, what is our goal? We would like to find the total mass of oil in the oil slick. And similar to one of the examples in the textbook, so if you have any challenges, take a look at that. What we're going to do is consider how to break this down. So as with other examples, we need to break it down into thin slices somehow. We're going to see a new slicing technique here. The reason we need a new technique is we have an area to cover, and vertical slices don't make a lot of sense. Why can't we use vertical slices? Well, if I asked you what's the mass of oil on this slice, there would be very little oil at the end here, lots more here because it's close to the center, and less later on. And so that's a pretty nasty way to try to figure out what the total mass is, because the slicing doesn't help us. So what we're going to do instead is imagine this oil slick again, and we're going to take a thin slice that is like a ribbon, a very thin ring, like so. This very thin ring is going to be incredibly helpful in finding the total volume, because we can take our whole area and slice it into many, many rings like this, and the total of all those rings will add up to the area of the circular oil slick. We'll do it all the way towards the middle as well. Okay. That will be our strategy. It's worth noting that we, again, have this problem that we can't find the total mass as density times area. Now that would be the tempting way again, because the units work out nicely. We want kilograms of oil, we have a density, we have an area, but the problem is that's not going to work because this density is changing. If I asked you, what's the density of the oil in this slick? Well, it depends on where you look. It depends on what R is. So we can't use this on a large scale, but what can we do instead? We can use this on a small scale. When we look at a small slice, in this case a circular slice, the density is constant. Roughly, and again that gets better as we use smaller and smaller slices. So what we can do with that is we can talk about the total mass on a slice, or the mass of oil on a slice. One of these rings, these thin ribbons here, and see how that works out. We'll get a little more formal here. The mass of oil on a slice at distance r from the center. So this is our arbitrary cut that we've used in other examples. We've got the distance r from the center, and unsurprisingly, the width of this slice is going to be delta r, so a very small change in radius. And on that ribbon, those are all points that are the same distance away, that would all then have the same r, so the same density, or close to the same density. Okay, so if we want the mass, now we can use that density, which will be 100 minus r squared. Actually, we'll do this in two stages. We'll write it out in words first. It'll be the density at the point r times the area in meters squared. Now, the density is straightforward. We actually have that in the question. Where it gets more interesting is where the area calculation comes in. There's a few different ways to do this. There's one very nice way, though, that makes this area calculation simple. If we take this ribbon and we unroll it, we unroll that ribbon so it looks like this. We cut it here, and then we unroll this end to be here, we unroll that end to be there. We keep then the thickness of that as delta R, and then what would be the length of it? Well, if I cut here and there's a radius of R, this side of the ribbon is going to be 2 pi R long. Now we're fudging just a hair. I'm hoping you feel there's something a little sketchy going on here. When we unroll something like this geometrically, there would be a little longer bit on one side and a little longer bit on the other side because the inner circle is a little bit smaller than the outer circle. But remember what we're doing next. We're going to let this delta R get smaller and smaller, and so that difference is going to get smaller and smaller. In fact, it's a very good approximation to talk about the area as if we cut this ribbon, unrolled it, and got a rectangle which has area 2 pi R times delta R. All right. If that's the case, then we can we're done writing out the mass of the oil on a slice. It'll be the density times the area of the slice. We imagine the area like this. We cut it, we unroll it, the thickness stays as delta R, and because we're talking about the circumference of a circle, not the area, but the circumference of this circle here, the unrolled length of that will be 2 pi R. Our next step, of course, is to put this into an integral format and evaluate it, but this is the single most challenging thing to derive in the problem. All right, so if we have one slice has 100 minus R squared over 10 times 2 pi R times delta R kilograms of oil, then the total mass will equal the integral of exactly that. We'll add up all those slices, and that will give us 100 minus R squared over 10 times 2 pi R times dr now. And the last thing is our limits of integration. Now these weren't actually given in the question like they were in some other examples, but if we take a look at our integral and ask ourselves, at what point does the density become unreasonable? If you look at how the density changes with radius, well, as R increases, the density goes down, and so R equals 0 is a good place to start. We'll start in the center. But at what point does it make sense to stop? I think it makes sense to stop when the density equals 0. And that happens when 100 minus R squared equals 0, when 100 is R squared, or at R equals 10. Only positive radii really makes sense here, so we'd use the positive 10 as our upper limit, and we'd see that on that last slice, right at the boundary here, we would have 100 minus 100, or 0 oil at that point. And that becomes our integral that computes the total mass of the oil in this slick. Having derived it, we can simply evaluate it now. Let's bring some constants out. We have a 2 over 10, that's 1 over 5. We also have a pi, so we have a pi over 5 out front from 0 to 10. And we can also bring this r into both of those terms. 100 minus r squared times r is r cubed dr. Okay, that's a simple enough form to integrate now. We can get pi over 5 times 100 r squared over 2 minus r to the 4th over 4, and that evaluated at 10 and 0. Pi over 5 multiplies everything. We have 100 times 10 squared over 2 minus 10 to the 4 over 4 minus the 0 goes in, and we end up with our usual 0 minus 0. Doesn't always happen, but it does happen when we're dealing with polynomials like this. And that gives us, if we get our calculator out, we can solve this. We will get 2,500 pi's, because we have 10,000 and 10,000 if you look at the cancellations. 2,500 over 5 times pi, or 500 pi's, or about 3 times that, so approximately 1,500 kilograms of oil. Okay, so that value comes from evaluating the integral. Where did the integral come from? That's the real challenge in these problems. That integral came from recognizing that we have a shape, we have a density we have a shape that's an area, we have a density that's kilograms per unit of area, but that we can't just multiply out what we were given times the area. That simply won't work because the values of the density are changing as we move from the center out towards the extremities. So we can't multiply by the density because there's multiple densities. What we do instead then is try to find a way to slice up the object so that the density is constant on that slice, and then we do our calculation from there.